Yeah, so my name is Brian O'Milan. I'm the head of software at a company called Creme Global. I'll give you a little background of what we are. And I'm joined today by my colleague, Roger Thomas, who's our chief technical architect there, and he's going to give you the science bit and the good bit of the conference. I'll hand you over to him in a little while. I'll start with a few bits of background about what we do and what we've learned along the journey, I guess, more importantly for you guys. So yeah, as I said, a bit of background for me. I'll talk a little bit about our data flow and our management of our data and how that's a problem and some of the things we've encountered that causes problems. Roger will, or maybe I'll cover some of the tech stack as well. Roger will talk about the validation of models and performance testing and how we keep a check on this all through the model development process and make sure it delivers what our customers needed. So yeah, very quick slide about our background. We do a lot of data science. We do it in the food industry mostly, some in the cosmetic industry. We do it to do things like some of the biggest companies in the world use our products to help them understand the impact of new products they're releasing on the general health and well-being of the population. And what we've found over the years is we've built several software platforms that do fundamentally the same thing. They allow our customers manage data, work with data that we curate, compare their results against our data sets, and run reports and models in the cloud to generate these results. So developed this several times in an array of languages, a vast array of languages. And a few years ago, we took the decision to move all this to a Python data stack. And we built this into a product we've called Expert Models. So this is all hosted AWS in the cloud. We use all the AWS goodness for scaling as it does well for users. We've built some of our own tools to do the scaling that we need for data science, which is this very peaky kind of high processor intensive scaling. And all of our front end then is Angular and served the back end served up through Django. So some of the things that we've found over the years is problems that may or may not resonate with you. If you've no data, we found, we originally built products where we let customers upload their own data, and we thought we'd just let it out there and see what they did. But that data part is a big value add that our products have. So we curate data and we present that to our customers to work with. And what we see in data science, I don't know how this feels for you, but the workflow is quite often broken. So what we've seen with companies we work with is their data science, if you want to call it, that's probably more like data analytics. It can often be done in Excel spreadsheets with a massive amount of formulas and arrays through that they email around to each other. Somebody somewhere changes a cell or a formula, no one knows what happened. The thing falls apart. We see this all the time, and the decision makers within those companies sort of say, can we have some sort of web app that does this data science for us? And to do that, the data scientist needs to learn a bunch of new tools. They might be Python experts and mathematical experts, but they need to learn front-end development. They need to learn SysOps, DevOps to kind of build this tool, and all of which is distracting them from their core work, which is generally the Python data science. We also see if there's no communication, there's no acceptance, and by that we mean if you don't understand what's happening inside the data science model, the business makers can be a little wary of the results it presents. So you need a good way of communicating what that is in the core. The deep knowledge needed, that is generally okay. The domain knowledge, people do know. They know what they're trying to solve with their data science problems. And the other thing we see, even some of the best data scientists have a very ad hoc development process. As software developers, we're all very used to using version control. Breaking our code up into nice modules so we can reuse certain parts of it. Some of the data scientists, particularly the ones that came from the academic background, can work on massive big scripts, and they do everything from take the data at the start to generate a PDF at the end, and it's all done in one giant script. Breaking that into something that's a little more version controlled and modular can really help. So I guess that was the brief kind of experiences of what we saw along the way. We've built a tool we called Expert Models to help us manage all that. It looks a little like Google Docs that can run big models in the cloud and work with the big data. I won't go into that today, but that's our solution to deliver our data science services so we can concentrate on what we feel is important, which is the Python data science at the kernel. I'm going to talk a bit about data flow, because this is the value that's in the product, you know, and I guess this is traditionally how a lot of our data science was done within Creme Global, and how it's changed. And what it would have been is we might have been contracted to, you know, generate a report for somebody, look at their data and create results. So we started with the raw data. We spent maybe half our time cleaning that data and making it something presentable. We combined that data with other data that we took from other sources to add the real value. We coded and reran and recoded our big scripts to generate some sort of report, which we visualized and then presented to their decision makers in the company. And they said that's great, you know, but what happens if we double sales next year? What is the impact down the line? And it was like, give us a week, we'll go back and we'll rerun everything. So I guess what we did at this stage was, you know, we write scripts for every single stage of this, so we can reproduce it at a moment's notice. And when you write scripts for every part of it, you may as well make it fully automated and take us out of the loop and let people work with it. So you present them with a web app, if you like, that has some of the parameters they might want to work with exposed, so that they can input new values and generate new reports on the fly. So I guess that's where we've moved from a more static style of data science to web apps where people can do their data science, or embed their knowledge into the applications. And part of the reproducibility part and the clean data part is just looking at how we do data ingestion better. Don't worry about all the boxes in here, but fundamentally we're trying to apply some of the DAMA guidelines, which say you should have good audited, governed practices for reproducing your data steps. So, you know, the cleaning of data part, where you're removing a lot of the bad data, you need to be able to step back and say, what was that bad data you moved? And by having scripts to do it versus just going into data sets and deleting stuff along the way is much more robust and much more audited and governed, and we can really reproduce that down the line. And when the board member says to us, where exactly did you get that result, we can step back and sort of say, we had these scripts to remove this data, and we did it with checking throughout, and we can be sure that the results we produce were the correct results. So with that note on just kind of good data management, I'm going to hand you over to my colleague Roger, who's going to go a little deeper.
Good morning, everyone. So my name's Roger. I've got around 6 years experience using Python as my primary language. About half of that time is kind of mainly the data science area. So today I kind of want to talk to you about how important it is, the concept of validation versus verification in data science with the view to Python. So what is verification versus validation? So in data science, verification is ensuring that, basically answering these three questions. Did we build the system right? Is the implementation of the system correct? Does the system produce the expected results given a set of inputs? And then validation is, did we build the right system to solve the problem? Is the system we are implementing correct? And do the results produced by the system actually describe reality? So do they describe the things we're trying to model? And there's a key difference between the two of them. Given an example, using, say, you want to develop a model to use polls in Britain to predict the outcome of Brexit. A good model probably would have predicted that Brexit wasn't going to happen. And if you'd given it some sample data and got the output that Brexit wasn't going to happen, you could say that your model is verified. Whereas actually what happened was, we all know about Brexit. It didn't happen. It did happen. So the model is not validated. So they don't often go hand in hand, and that's just an example of the difference between verification versus validation. So verification is easy. It's easy to verify a model. If your model is adding two numbers together, you can 2 + 2 should equal 4. That's the easy part. So unit testing and integration testing. The validation is hard. Obviously, there's no such thing in Python as self-data assert this model accurately predicts models of reality. That there's no such thing as that. So for this talk, we'll focus more on verification, because that's the easy part. So verification is protection. If you're a developer and you're working in data science, it's really important that you write code to verify the data science projects that you're working on. So it makes you ensure that the things that you write aren't broken. So given a scenario like this, so someone comes to you saying, say you're working in financial trading, your model does some sort of analysis of the markets and gives results to your users to help predict what things they should buy or sell. So the system is too slow. We need to run it faster so we can you can trade faster with our competitors. So I mean, one solution, I know it's a bit trivial and doesn't really make much sense, but I mean, you could just go in there and return a random number. I know that might sound a bit crazy, but some of the requests that we get from our customers are so bizarre and so specific. Sometimes I think that you could just put a random generator in and they wouldn't even know the difference. But not really. They'd probably kill me for saying that. So obviously you can't just do that. So if you want to go in there and but yeah, so if you do that random number generator thing, you go back to your unit test and everything should fail. So you can't just do that. But you want to go in there and do stuff faster, and now you can, with that refactoring, you're confident that you're still getting the same result given, your two inputs. So yeah, I mean, a lot of this is done using unit testing and mocking, but I mean, mocking is dangerous because no matter how well you write unit tests and how well you use mock libraries, you're never really accurately describing how things run for your end users. So it's really important to write integration tests. And I thought I'd just put a picture of a goat up there because it seems like you can't really talk about Python without a beta testing goat being in there somewhere. What the thing to do is to write a suite of integration tests, which is really important for writing models. So using example data that you kind of have, that you should verify independently, you can use integration tests then to make sure that your system is accurately describing and producing the results that you want given the model spec or the spec of whatever you're trying to create. If you're not doing this right now, you really should. If you're in data science and you're not, writing model verification tests or verification tests in general, you really should be, because you've no other way of assuring that the science is always correct. And if you do start doing this, you really will thank yourself later. So obviously, it's for a large part of this is version control. Everything you do in data science should be in version control. All your tests should be in there. If the numbers change, it should be easy for you to see the difference of the numbers. So if your model produces, a CSV output or, a graph or something like that, you should try and make it easy to see the diff between the different results given a change that you've implemented it in your spec or your design. Sometimes, so the outputs of a model or a data science project do change between code versions, and these can be innocent changes, and you want to be able to track these. So, for example, if a customer says, "Oh, I want less precision in a number," then your model test will, or your verification test will change, but they're changing innocently. So you want to be able to track them to kind of tell the difference between the changes that you expect and that should happen, and the changes that happen without that you don't want. So these differences between innocent and non-innocent changes must be tracked and understood. Otherwise, you just don't have a good view on your model and what it's doing. So another part of this that's really important is performance testing. So if the system is too slow and we need to run faster so we can trade with our competitors, you might go in there and look at speeding it up using NumPy or something like that. But then, you might look in a certain instance that it looks to be running faster. A unit test might assert that it's running faster, but you don't really know if the speed up is sufficient enough for what you're trying to solve, and if it's sufficient enough given expected data. Like unit tests are great and everything, but a lot of time, especially in data science, when you're programming, you can write tests with example data that you kind of know the system is able to handle, but really what you should be doing is testing your data science project with inputs that are it's likely to encounter every day. So that's where performance testing comes is really important and should come in any kind of data science project. So that's where performance testing comes in. So I mean, it's pretty easy. The outlining of the approach to performance testing. You take a timestamp before the function, run it, and then you assert that a certain amount of time has passed between that function being called. And a lot of it's really important to get a good view on how your code and how your project runs on the actual hardware, again, that you're going to be using in production. So when you put your data science project in production, you need to be able to monitor how it performs, to the end user. So again, unit tests don't really do that for you. You need to be able to write verification and integration tests. So you can monitor how your project or your data science project actually runs in the real world. So the benefits of writing verification tests and integration tests are numerous. I mean, say you want to go in after you've working on a data science project for 2 years, and you go back and look at the code, and you're like, oh, this is pretty ugly. I think I'll go in and try to refactor this now. But refactors obviously shouldn't affect the results or performance. So I mean, if you update a function or make some changes in your code, that shouldn't affect the numbers, and it shouldn't affect the performance at all. So that's where integration tests and performance tests come in, especially if you're dealing with a lot of customers where the numbers and the performance are most important. Like a lot of the times with data science, there's like a fancy GUI on top or UI. I mean, having fancy GUIs and UIs are great and everything, but if the numbers aren't if the numbers aren't correct and they don't happen as fast as the user or customer wants, then all the fancy GUIs and UIs don't mean a thing because the numbers are wrong. So the benefits of these are refactoring with confidence, and then after refactor, how do you know that it's still fast enough for the customers? And that's where the performance tests come in. Again, some more benefits and enhancements. So enhancements and feature requests. So you begin a data science project with a problem to solve, but as time goes on, that problem evolves, and you need to solve it in a different way or maybe with different variables. So you need to go and change the outputs. So now our function AB doesn't return C anymore, it returns D. And how do we know that the code is now producing the correct numbers? So you have to go in there and then update your verification tests and your integration tests. And without a good suite of performance tests and verification tests, you just don't know if this has been done correctly. Maybe it's still producing C given A and B, and as a data scientist, you just can't release these kind of things to production with confidence if you don't have these tests in place. So what are the tools and tech that you can use to write these kind of verification tests? So you need to use automation software like Jenkins, Maven, or Travis. So every time code is pushed to your code base, whether it's a personal project or you're working for a multinational company, every single change should be monitored, and your performance and integration tests should be run ideally before any of this Python code goes into your production. I mean, all your performance tests and your integration tests should be passing. And as a developer, you don't want to be spending most of your time running these things. So that's where automation software comes in, like Jenkins, Maven, and Travis. And these things should be running at every single time a change to your code is being made. So again, cloud computing services are really handy for this, like AWS and Rackspace. So you can check out, a certain image or a certain instance on Amazon, and you know that if the performance is no longer the same as it used to be for that exact hardware, nothing else has changed, so it has to be your code. So then you know that your performance has regressed, and then that means that you can't push this code, so you have to go back and change things. So yeah, I mean, so again, using stuff like Git, you need these tools to know if you can merge your branch into master or not. And then after that, after you do that, so the code might look fine and everything. You got your approvals from your peers, using pull requests or whatever, so the code looks great. But you still need to assert that the numbers are still correct, and is it sufficiently performant? Does it still do the number crunching in the time that you want it to? So this is kind of a graph of who's responsible for what. So the validation side that we talked about earlier, that's really the role of the data scientist, and the verification is more the role of the developers. A lot of the times there's people are in the middle, like myself, who kind of do both. But just to again come back to that difference between the two of them, the validation steps are more for the data scientist, and the verification side is more for the responsibility of the developer. So your implementation of a piece of data science and how it performs and the numbers that it produces, that's the role of the developer, whereas the role of the data scientist is to come up with that project itself. But a lot of the times, these two things are the same. So wrapping it up, that's the end of the talk really. Python is awesome at everything, data science and automation. Verification tests are really important. If you're not doing them from start to finish, you really should be, because otherwise you just don't know. You can't guarantee that whatever you're implementing is going to satisfy your customers in terms of what the project is producing in terms of numbers, and is it running as fast as your customers want it to. I mean, these things have to be done before you can put them into production. Otherwise, they're just going to come back and your customer is going to say this is wrong or it doesn't run fast enough. So these things should be in place before you even start working on a project, or before you even start considering putting it into production. Everything must be verified. That's me done. Thank you for listening, and if you have any questions, please go ahead.
Thanks for talking. Any questions?
I'm just curious, what kind of verification test? Thank you very much for your speech, and
Sure.
My name's Sergey. And what kind of verification tests are you doing? Because usually when we do some kind of machine learning, it is just analyzing the difference between when we teach some algorithm, it's just analyzing difference between right answer and predicted answer.
Sure.
And it is just some percentage or then in your verification test, you just expect some kind of differences, or because usually your data set, let's say, has 100 points and 100 answers. And then inside verification test, what are you checking? What are you compare?
Sure. I mean, unless you're working in like using some sort of randomness, like non-deterministic programming, and even then it can be solved with seeding. But I mean, because computers are deterministic, you can feed it a set of inputs that should give a certain output. So it's basically just supplying a sample data set that given that, like pushing that sample data set to that model or that function should give you a certain output. You know what I mean? So it's really just taking a test case that your model is supposed to accurately describe, and then verifying that independently. So yeah, with machine learning, it might be more tricky to come up with an actual test case, but it's just really a case of feeding in sample data sets and verifying that it's literally just a case of verifying that the output of that matches an output that you've saved somewhere, whether in a database or a local file. Does that answer your question? Okay, cool.
More questions?
Hi. You were talking about performance testing there, and one thing I think is very difficult, and maybe you have some tips about this, is I develop locally, and then maybe I push something to a CI pipeline, and then the tests run again.
Sure.
And then it's pushed to probably somewhere that's slightly different from where your CI pipeline is running. You don't want it to be different. But all those will have different performance characteristics. How do you work around that?
Yeah, so I mean, really, it doesn't matter the performance, running locally on your MacBook or whatever versus running on your dev server. That doesn't really matter because your users aren't using that, you know what I mean? So really you should be testing the performance of your system when it is actually released into production. Whether that be you either have a there's two different ways of doing it. I guess you either have a different environment that completely describes is the exact same setup as your production environment, so you can either do your testing there, or if your production can handle this kind of testing, then you just literally do it against your production environment. Otherwise, you just don't know, because then user comes along and says, oh, this request is taking way too long, or this model is taking way too long. And then you go, oh, but it runs in 1 second on my machine, but then that doesn't matter. It's your machine, It has to be tested against what the end user is using. Otherwise, it doesn't matter.
Hi, a quick question. So in your chart you showed earlier, the data is loaded from local machine like Excel and CSV into your platform.
Sure.
So my question, for example, for enterprise, they won't allow users to have data in their local machines. They like to load data from the other database or even Hadoop. So what's the best options on how that data pipeline works?
It really depends on your environment. I mean, there's tons of different tools out there for data loading. I mean, like AWS itself has tons of options for stuff like that, like Kineticist or whatever it's called. But I mean, like, what data are you talking about? What kind of, like, can you give an example maybe?
For example, two types. One type would be traditional database, any kind of the data from the MySQL or Microsoft SQL, or maybe from the Hive table seen on the Hadoop. So any kind of the other options or packages or tools can load from multi-source.
From not that I know of. I mean, like, do you have any?
So I guess you're asking, you've got data coming from lots of different sources that you want to use in your tools. As Roger's saying, that there is tools out there. We tend to go bespoke for that. For our data ingestion, we'll write modules for each thing. A tool I quite like is Data IQ. If you've seen it, it's a data science platform they've got that they're very strong in the workflow, and the outputs of some models can form the inputs to others, but you can define the workflow in a nice diagram, and you can visualize what's happening at each step, from the raw data coming in through the cleaning, through an initial model that might pull out some key parameters. So yeah, I guess there's tools out there. Data IQ is one you might look at for doing the data ingestion, but we go bespoke a lot. Our customers tend to have very specific data sets, or we curate data sets that we pull from data providers, and we manage those and turn them into something that's clean and can be correlated with other data sets.
Okay, cool, thanks.